So let's move on to the second track of the predictive world model. And the reason for us to propose the predictive world model challenge in this year is because we wish to figure out a way towards the autonomous machine intelligence by using the world model. Because as illustrated by previous presenters, they all mentioned that the predictive world model is useful for building a simulator and use the simulator to train the RL agent or whatever agent. And actually, in this track, we wish to figure out whether we can directly use the predictive world model as the intelligence itself, whether we can use the mean of predictive by prediction pre-training, whether we can obtain a good intelligent agent to obtain the autonomous driving instead of trained by simulation. So in summary, we think that if we can use the predictive world model, if we can use prediction pre-training, maybe we can enable the intelligent agent to perceive the world that learns to react. And as a result, maybe we can obtain an agent to learn a way to study the counterfactual problem, which is the third stage of the human evolution as shown in the right. That is, if we have the ability of counterfactual imagination, maybe we can develop new things, maybe we can let our agent be better than humans. So another reason for proposed challenges because we have already proved in this CVPR that if we use the mean of predictive work by prediction pre-training, we can obtain a huge improvement in perception, prediction, and planning for planning. So this is another reason for us to propose this challenge. And we need to see whether we can use large scale of Newton data and whether we can obtain a foundation models for the end-to-end autonomous driving. So this is a second reason for proposing this track. And to be specific, in this track, the inputs of our model is the multi-view images in historical 3 seconds. Given the Newton, the frame rate of Newton is 2 Hz, so there are 6 frames in the historical images. And the output are future point clouds in future 3 seconds. The reason for us to use to predict future point clouds from historical images is because we wish the model to learn how to build up the 3D geometry from the image, and then how to model the dynamic of the future dynamic, how to model the temporal inference for future dynamics. And the metric for this track is transfer distance within the range of minus 51.2 meters to 51.2 meters. So here is a summary of the challenge stats. We receive a lot of attention, so this is a new track in this year. We have 69 teams from 13 countries ranging from academic to industry. And we obtain solid improvements compared to the baseline. And also congratulations to the first place, which is a team from University of Science and Technology of China, and the innovation award and the innovative award is a team from Huawei and the Chinese University of Hong Kong Shenzhen. And the reason for give the innovative award to the second place team is because from the award committee is that their method is distinct. It's a distinct baseline to the official baseline, and they improve the speed of the point cloud prediction by decoupling the point cloud prediction to the occupancy prediction and flow estimation. And unfortunately, the team member of the second team cannot make it to present their method on in person to us, so they carefully prepare a video to us, and so let's see the video. Chinese University.
Background. Serving as an abstract spatial temporal representation of reality, the world model can predict future states based on the current state. The learning process of world models has the potential to provide a pre-trained foundation model for autonomous driving and also can be a world simulator. This challenge simplifies the world model as a new visual point cloud forecasting task. Given vision-only inputs, the neural network outputs point clouds in the future to testify its predictive capability of the world. The challenges of this task can be concluded from three aspects. First of all, we need to learn the cross-modality knowledge since the inputs are the 2D visual images, while the outputs are the geometric 3D point clouds. Second, it requires the model learn the temporal dependencies and forecast the future states. Finally, the training samples of this challenge are so huge that we should design an efficient approach to consume the huge dataset in an acceptable time. As a newly proposed task, there is only one baseline solution VDAR. By introducing the latent rendering and future decoder, the VDAR could forecast future point clouds with visual images inputs only. However, VDAR is a training-unfriendly method as it demands long-time training with the high computation resources consumption. Besides, the autoregressive manner could not capture temporal dependencies enough, and the implicit decoding in VDAR could not maintain the explicit temporal consistency. Therefore, we reformulate the visual point cloud forecasting task as a 4D occupancy forecasting task. By taking the multi-view images as inputs, we firstly use an occupancy prediction model to predict occupancy, and then the carefully designed occupancy world model is utilized to forecast the future occupancy volume. After applying the rendering operation, we can obtain the future point cloud. For the occupancy prediction model, it has been well studied, and we adapt the LSS-based method BEV-DET as our occupancy prediction model. The other popular occupancy prediction approaches like BEV-Former and FBOCC are feasible as well. There are only a few recent efforts exploring the occupancy world model. Despite having the ability to be able to predict future occupancy, OCC world requires 2 stages of training. The first stage of training is unstable and severely affects the final performance. The second stage of iterative prediction does not take into account the spatial structure and temporal dynamics of occupancy. To overcome the aforementioned issues, we propose a novel occupancy world model, the D2 world. It is an end-to-end single-stage 4D occupancy forecasting pipeline and is able to simultaneously forecast multi-frame future occupancy in a non-autoregressive manner. And in order to make full use of the inherent spatial structure of occupancy, we leverage the flow information in our pipeline to further alleviate the forecasting problem. The historical 3D occupancy is pre-processed into BV-map and then becomes into spacetime tokens after feature extraction. The spatial temporal transformer is utilized to capture the spatial and temporal dependencies, which is consisting of multiple spatial-aware local temporal attention blocks. After that, we leverage another spatial temporal transformer as flow decoder to forecast the flow information in each future timestamps. In this case, we could apply the warping and refinement operations to transform the current frame occupancy to obtain the future occupancy more easily. Considering the required future point clouds only contain 3D geometric structures, we choose to forecast future occupancy density volumes. Finally, the future point clouds can be obtained by rendering from these future occupancy volumes. Unlike the images containing redundant information, the occupancy is a high-struct and compact representation, so we introduce spatial-aware local temporal attention block for spatial temporal feature extraction. It has similar structure with vanilla attention, except that we utilize the 2D convolutions to retain the structural information rather than the MLPs. And the 3D CNN is used to replace the original FFN layer for capturing the local short-term variations. When designing our occupancy forecasting model, we found that most of the voxels in next frame could be easily derived from last frame, since most of them are static. So we choose to forecast the future flow map to alleviate the occupancy forecasting process. Further, we could leverage the occupancy semantics information to decouple static and dynamic grids, and then the flow map can be only applied on these dynamic voxels for better forecasting. Specifically, the flow decoder forecasts the future absolute flow maps with respect to the current frame. And we can use the future ego poses to current ego pose transformation to transform the flows and then warping current frame to all future frames. In actual implementation, we force the flow of static voxels to be 0 before warping. After that, A simple refinement module is utilized to revise the warped features. Therefore, this is our whole pipeline, including occupancy prediction stage and 4D occupancy forecasting stage. The optimization losses of stage 2 are the same with VDAR, and without any other tricks and models ensemble, we achieve competitive performances. The dataset of this challenge is OpenScene dataset, which contains more than 0.6 million full training frames and 40,000 mini training frames. Each frame has 8 multi-view images. The chamfer distance is used to evaluate the point similarity of forecasting point clouds and ground truth. The lower the better. And the other experimental settings are listed here. According to the challenge's rule, we use 6 historical visual frames to forecast future 6-point clouds frames, and the size of input images is 512 times 1408. The BEV-DET with Swin transformer base as the image backbone is leveraged as our occupancy prediction model. And different with original BEV-DET, we use the class Waith-Cross entropy loss and the low-VAS softmax loss to improve performance. We train both stages within 24 epochs. Here are our point cloud forecasting performances. It is obvious that our method achieves state-of-the-art performances. Specifically, when training our model in the 1/8 mini training data, our model could obtain average 0.71 chamfer distance, while the VDAR baseline only achieved 1.58. Although without using the flow forecasting strategy, our method still obtains 0.89 chamfer distance. It validates the effectiveness of reformulation of 4D occupancy forecasting for solving this problem. In order to submit the results to the online benchmark, we additionally train an occupancy prediction model. Our best results achieve 0.79 average chamfer distance and rank second place in the leaderboard. This is a screenshot of our results in the official leaderboard. Although the performance of our method is slightly lower than first place, our efficient method has potential to extend to large-scale dataset. To compare the training efficiency of our method with VDAR, we compute the training hours and GPU memory usage for each method. From the results, we can easily find that baseline requires both long training hours and high GPU memory. In comparison, our world model requires much few training hours and acceptable GPU memory. And despite our training time is mainly spent in stage I for obtaining better occupancy prediction performance, this module already existed in modern autonomous driving systems and can be also as our world model's inputs. Conclude our work. We reformulate the visual point cloud forecasting task as a 4D occupancy forecasting task and propose a novel and flexible framework with decoupled dynamic flow in a non-autoregressive manner. The experimental results show that our method could achieve competitive performances and require less computation resources and much few training time as well. Although impressive, our method still needs further exploration. For example, the stage 1 and stage 2 could be end-to-end training for optimization, and we can further explore the performances of scaling up image backbone and world model networks. The code of our method will be released in GitHub. Please stay tuned. Here are some selected references. Thanks for watching.
Okay, sorry for the display error. My name is Zhenxin Li, and I'm very happy to represent Team NVIDIA to share our first place solution, Hydra MDP, for this end-to-end driving at scale challenge. Okay, so our introduction mainly consists of 4 parts. We'll first talk about the background, and then our solution. Then we'll talk about the experiments and the conclusion. And Igor has just introduced the SnapSim dataset. So basically, the datasets that were previously used to benchmark end-to-end planners, they they have a lot of problems. For example, the major paradigm was imitation learning, and these methods are all very vulnerable, and the metrics like imitation errors that are employed to evaluate these planners are also biased. So NAFSIM here evaluates the planner with simulation-based metrics that can actually take into account how safe your planner's output is. And before HydroMDP, we conclude two prevailing paradigms. The first paradigm is called single model planning and single target learning. So basically, the model regresses a single trajectory, and we use the log replay trajectory that acts as the only positive sample to supervise the model's prediction. And the major problem is that the model receives very limited supervision from log replays because there is only one single positive sample. And the second paradigm is called multi-model planning plus single target learning. So basically, the model predicts multiple trajectories instead of one trajectory, which is also supervised by the single log replay trajectory. So it also faces the same problem as the previous paradigm. And the second problem is that it often uses non-differentiable post-processing to select the best trajectory based on the model's perception output. And the problem with this is that if your model's perception is imperfect, then it harms the final planning. And also, this process is detached from the neural network, so it does not really align with the spirit of an end-to-end model. And here we propose our third paradigm, which is multi-model planning plus multi-target learning. So apart from a single log replay trajectory we use to supervise our end-to-end planner, we also use a rule-based simulation engine to generate multiple trajectories, which are also used to supervise the planner. And since these generated trajectories are from a rule-based engine, so these trajectories are safe for each scenario. And the other benefit is that we integrate ground truth perception in training the planner instead of resorting to some non-differentiable processing techniques. So this is our overall architecture, and there are three parts for our architecture. There is this perception network, and there is a trajectory decoder that generates multiple trajectories. And we also, our major novelty here is this multi-target hydra distillation. For our perception network, we use this transducer, which is the official baseline in the NAFSIM challenge. And for the trajectory decoder, we have this a fixed planning vocabulary that contains about 4,000 or 8,000 trajectories that are sampled from the new plan database. And we use a distance-based imitation loss to supervise this whole planning vocabulary. So in order to reward the trajectories that are very close to human drivers' behaviors. And then for the multi-target hydra distillation, it basically consists of two steps. The first step is the simulation of the entire planning vocabulary with ground truth perceptions, so that we can see here for each metric, we have a set of trajectories that best fit this metric. And we have a set of hydra prediction heads which are trained to fit these rule-based teachers. So the advantages of multi-target hydra distillation is that it does not rely on non-differentiable post-processing techniques, and it can also bring sufficient supervision for the entire planning vocabulary, because previously, if we use imitation learning, then we only have one positive sample. And the third benefit is that the ground truth perception can foster planning in an end-to-end fashion. And during inference, since our model cannot fit each teacher perfectly, we use a weighted sum of all of these confidence scores to calculate the final cost. And we find that in this NAFSIM challenge, it is necessary to prioritize rule-based costs over imitation because the metrics of this challenge does not take into account how close you are to the log replay trajectory. And here are some experiments. We find three things that we think are very important. The first thing is that if we employ a larger planning vocabulary, the method can yield better performance. It's basically because if you have a larger vocabulary, then you have more candidates for the model to choose from. And the second thing is that if we try to teach the model to fit the overall PDM score, it leads to degradation in the final performance. And I believe it is because the overall PDM score is too random and it's too complex for the model to learn. So this also suggests the necessity of our multi-target learning paradigm. And the third thing we find is that if we involve an extra single learning target, we can get improvements on this corresponding metric. So this also demonstrates the scalability of our methods. So we can involve more traffic rules or like traffic lights or traffic signs in our model, and we can scale our model in that way. So finally, under the same setting, our version surpasses the baseline by 8.5% in the overall PDM score. And the other part of experiments is that we try to scale our model up with larger backbones and larger input resolutions, because previous literature like UniAD, it suggests that if we use large image backbones, it only leads to minor improvements in the final planning performance. And here we use larger backbones and we use larger resolution, and we can find that our methods reach a higher PDM score. And here are some visualizations. And for this one, we can see that the lanes here are very different. There are these small metal humps. However, our model can understand the map structure and stick to the lane it is driving on. And the second thing is our model here is trying to overtake a long-tailed object, which is a utility car that is probably traveling very slowly. And we can see our model here is trying to move to the right lane to surpass this object. And the third thing is also a very interesting example. I think basically the Eagle vehicle is placed at the center of two lanes. So even for human drivers, we may not be able to predict whether the model is going to the left lane and make left turn or going to the right lane and make right turn. And this is the ambiguity in intentions. And we can see that our model here is slowly moving to the right lane and make a right turn instead of going in the middle of these two lanes. And that's basically our presentation. We have presented HydroMDP, which is a teacher-student model leveraging human and rule-based teachers. And it is also a framework that learns how the environment influences planning in an end-to-end manner. And HydroMDP achieves the state-of-the-art performance on NAVSIM. And we want to thank all the contributors and the entire NVIDIA team. And that's our presentation. Thank you.
And in this year's challenging except those check on autonomous driving, we do have a check on embodied AI, the multi-week 3D grounding track, and I will give us some introduction.
Hello, everyone. I'm Tai from Open Rover Lab. It's a great pleasure to be here to introduce this new track, multi-view 3D view grounding. And this is a new track that is coordinated with Open Drive Lab. And now let me introduce this track. First, let's have a brief review of this roadmap on 3D perception. As we all know, 3D perception for off driving and also indoor scenes have made great progress in past few years. There are many popular datasets and benchmarks, such as KT New Scenes, Lyft Waymo Argoverse for off driving, and StarGD ScanNet 3R scan, multiple 3D, HM 3D for indoor scenes in the global view perception. And now transferring from the object driving to indoor embodied AI. As we all know, it's asked for learning interaction, learning from the interaction. The embodied AI needs more multimodal, egocentric 3D perception for holistic scene understanding in enclosure space. So we established embodied scan that is collected from the previous raw data in ScanS, 3R scan, multiple 3D, and then annotate over 1 million language prompts and 160,000 instances with oriented poses. And for different perception tasks, including 3D detection, occupancy prediction, and real grounding. And also for egocentric inputs, we also support monocular image, multi-view images, and continuous frame. So in this track, we mainly focus on multi-view 3D view grounding, and the setup is the model is selected to take the multi-view images input given a language prompt about the target object and output the grounded objects that is represented with a 3D bounding box. The metric is a conventional 3D LU-based accuracy that is similar to 3D detection. And there are some statistics for this track. There are also lots of tension on the newly introduced tasks from over 60 teams, participants, or 12 countries, regions, and 150 submissions. We also observe a solid improvement by the outstanding champion, and we will welcome the winner team to introduce next. And so congratulations to the first two teams from Tsinghua University and Lenovo and Xiaomi Robot. Last, we will introduce what's next from our team. That is follow-up of embodied scan to build a multimodal 3D dataset with hierarchical language annotations for pushing forward the training of 3D LLMs. Maybe no voice. It is the largest ever multimodal 3D scene dataset with hierarchical grounding language annotations. That you can see the model trained with this dataset. It can achieve basic grounding and dialogue abilities from 3D LLM. You can see some counting problems and also description for objects and regions. Sometimes we need to distinguish different objects from a long video. For example, here distinguish from the white and black chairs in the room. So this is a data set that is built upon the previous embodied scan, but more focused on hierarchical grounding annotations for different aspects of these things. And also the language prompts are more complex. So because the time is limited, please see more details from our project page and our paper. So next, let's give the time to the winning team and welcome Jiaheng to sharing their solutions. Thank you.
Hi, good afternoon, everyone. I'm here to represent my team from Tsinghua University and Lenovo AI Lab to present our solution for the multi-view 3D grounding challenge. So our solution is called DenseG, alleviating vision language feature sparsity in multi-view 3D visual grounding. And it's presented by me, I'm Henry Zhang, and our team consists of people from Tsinghua University Leap Lab and Lenovo AI Lab. First, I'll discuss backgrounds related to this challenge, and then I'll show some motivations that we develop our method, and then we'll discuss our method and experiments. So first, the multi-view visual grounding, it aims to locate objects in a 3D scene based on the natural language description. It is a fundamental task of embodied multimodal 3D perception, and as Taiwan discussed, I won't discuss this again. And the baseline that we use is the embodied scan, also discussed earlier. So basically, we have a visual inputs, the point cloud and multi-view image sequence. Then we get a language prompt. Then we have to locate the object in the scene following the language prompt. So the some problems we found in the previous methods is that they use a scene level inputs from the global view, and embodied scan improves it by using real scan inputs from multi-view, which is more like a real life data sets. But the problem here is the way that the embodied scan fuses the visual inputs is through a sparse fusion method. And this method, the problem is, let's say for a small object, only a very few point clouds will be representing this small object in the point in the scene. So it is very difficult to identify this object in a point cloud with such few point clouds. But it is easily recognizable in the RGB images. So the motivation is, of course, what we said earlier, lack of to the visual sparsity problem, and then another one is the language sparsity problem. Let's say there is a prompt, find the chair beside the table, but as you can see in the scene, there's a lot of chairs, which is very is a ambiguous prompt. There are some cases that has this kind of prompts. So we improve it by giving more context to the models. So, of course, insufficient anchors, it can lead to ambiguity in localization. And then, of course, the language context is insufficient. So with these motivations, we develop our method. Here's an overview. First, for the language model, we first perform augmentation by using LLM. Then we develop a by TV module that enhances the visual features. So for the LLM augmentation, there's 3 steps. First, we construct a scene info database. For this scene info database, from the original data set for the same scene, we collect all the language prompts. Then we formulate a scene info database. Then this provides a context for LLM to augment the text prompts given to it. And then, of course, we want to make sure that it is consistent with the info database. So we verify the results again using LLM. So the prompt principles are, we want it to be sufficient and reliable anchors. And then, of course, we so we follow a view refer to use an opposite view only for view dependent text. And then, of course, we want a high confidence for the anchors. And then we also propose another module called by TV. This is to enhance our visual features. So what we did is first we extract the global features from each of the views, and then from the views, we perform self-attention for interaction between views. Then we perform cross-attention with the text models, and then it's to reduce the multi-view semantic information loss during the 2D 3D fusion, because we already extract the 2D features and then we add it back to the fusion module. And for our results, we use we follow the embodied scan, so we didn't change the backbones, and we use the ResNet 50 for a 2D backbone, the Minkowski-net 34 for the 3D backbone. And then for the text backbone, we changed from Roberta to Clip. Then, as seen on the mini validation data, 1/5 of the full data, by simply replacing the Clip encoder, we already gain around 1% MAP improvement, as shown on the left column. Then with our LLM augmentation, we achieved 3% MAP improvements. And then for ByTV, we have another 1% gain. And then for the full data set, just by using this, we are trained on 8 epochs. We have 47.23, and then ensembling different models, we get a 59.59 MAP for the IOU 0.95. And with this result, we got to the top one in this challenge. And some tricks we use, these are the tricks that we found most helpful in our method. One is CVGS, the class balancing, grouping and sampling. This is during the pre-training stage. We for the object detection, we do a balancing for the long tail distribution of classes. So this kind of alleviates the long tail problem. Then we also use an NMS-based ensemble. That's what we use for the final model we use to submit to the leaderboard. So as a conclusion, we propose the DenseG. For the language modality, we enrich the language prompts via a scene information database and LLMs to reduce the negative impact of distractors. For the visual modality, we propose a ByTV module, the text and view image interaction module, to reduce the loss of multi-view semantic information. And here are my collaborators. We thank them for the contributions to this work. And if you want to know about work from our lab, THU Lib Lab, you can scan the QR code to visit our GitHub. Thank you.
And here we come to the last year in the morning, the occupancy and flow check. Now in the last year challenge, the occupancy check, the most attention worldwide. So this year we keep it and we add some additional flow annotation to the data set, and Jiajun will give us some more detail.
As this is the last track in the morning, so it will be very quick. Okay. So the 3D occupancy, the motivation of introducing this test is the problem of the current commonly used 3D representations, like the 3D boxes, bounding boxes. The 3D bounding boxes closely represents the geometry shapes and the position of the objects in the scene. However, it easily ignores the fine-grained and detailed geometry shapes of the irregular object or open-world objects. Instead, 3D occupancy greatly catches the geometry shapes in a unified manner by representing the objects in the scene as a set of voxels, whether occupied or not. As a complementary representation, flow also captures the dynamics of the whole scene. That is a vector of each voxel. And the occupancy and flow has also been integrated in commercial solutions like the Mobile Eyes and Tesla. So for this challenge, our evaluation metrics include two parts: the occupancy prediction. For occupancy prediction we use MIOU, which is commonly used for cementation. And for flow prediction, we easily adapt the L2 distance of the predicted and ground truth flow. The final evaluation metrics was the average, weighted average of the both metrics. So we would also like to thank our collaborator Livewell AI for presenting their good data set Livewell occupancy, which can be used to augment the data diversity of the nuisance data set. For the challenge status, we have in total 97 teams this year from 17 different countries and regions, and there are a total 153 submissions in this track. And the outstanding champion goes to the IEIT team, and the honorable runner-up goes to the Harbor Chips teams. Congratulations. So due to the time limits, we will leave the solution of the winner during the lunch break, and please come back at the 1:30 p.m.